ratio tables. Again, one big key on that. As soon as I say ratio table, you automatically know that everything in it is equivalent. That's the definition of a ratio table, because they are all proportionate. So we're going to be creating and reasoning about tables of equivalent ratios, and we're going to use known values to determine equivalent ratios. We're also going to go through solving problems by the reasoning about diagrams. Don't know that we'll get to that part today. Our first question is a review from last lesson. So you have a cup of milk to make a batch of 8 pancakes. You have several different ways you can set this up. One of the first ones would be the fractions like we did on the last part of last night's homework. So I just start 1 cup of milk over 8 pancakes.
So we're writing this. Everyone should be
equals, and then I just put cup and pancakes. The additional information they gave us was 16. So all I need to do is say, how do I go from 8 to 16? Times 2, so what am I going to do at the top? Times 2. So what's my answer? 2 cups of milk. Now, all of these are going to go the same way. We could also do a tape diagram. So if I did a tape diagram, I've got 1 box and then 8 boxes. 2, 3, 4, 5, 6, 7, 8. So this one would be the milk and the pancakes. And anytime we do abbreviations, you need to have a key so that you know exactly what those are. So on this one, I'm going from 8 pancakes down to 4 pancakes. So what would my ratio constant be? No, it's going the other way. 1/2. So, is it okay to have a 1/2 as a ratio constant? It's absolutely fine, guys. But once I found it, every box gets it. So if everyone in the pancakes has a 1/2, that gives me 4. So how many cups of milk is it? 1/2. So you can either write it as 0.5 or 1/2. So there's my answer. And I'm not going to do a double number line on this one. I'm going to go back to the first one. So I have 4 cups. Actually, I'm going to use my abbreviations from my key. 4 milk over, nope, start with my base, sorry. 1 milk, 8 pancakes equals milk and pancakes, but now I know it's 4 cups of milk. 1 to 4, I did times 4, so I go 8 times 4 and I get 32. So 32 pancakes. Any questions on any of those 3? You understand the setup? Okay? Guys, the whole key on this, because we're doing mathematics with our ratios now, the fraction format is your best way to do them. Okay, we're going to talk now about population density. This is a special ratio that compares people to square miles. So this one gives the approximate population density for 4 U.S. states in 2019. Which of the states has the greatest population density? Which state has the least population density? Explain what this means in your own words. Number 2, what's the population density of your state? We're not going to do that one because we don't live in the states. But I will tell you, you do need to use your key in order to figure out how to set these up. So first period really struggle on this. I'll give you a little extra hint. It's best to set them up as a ratio first and then go to a unit ratio, meaning that my denominator is 1. Okay? So we'll give you guys about 7 minutes. See if you can figure these out. Use your key to set your ratio up. And once you have your ratio set up, then you can solve it mathematically to figure out which one has the most, which one has the least. Okay, good luck. Okay, I'm already seeing people struggle. So let me do the first one for you to give you an example.
There we go.
How many figures are there? 1. So from my key, that is 200 people. How many boxes are there? 5. From my key, that 1 is 1 square mile, so that means that is 5 square miles. I'll give you a big hint. In order to do a comparison, it's best to go to my unit rate, meaning my denominator is 1. So if I go to a denominator of 1, how did I go from 5 to 1? Divide by 5. So what am I going to do to the top? Divide by 5, which gives me 40 people. So now I have a basis to start comparing the other ones. So I've done 1, you have 3 more to do. Just a couple hints. This is the same as 3/4 of a person. This is the same as half of a person, meaning I take either half of that number or 3/4 of that number for that piece of the figure. Okay? So again, we'll give you about 7 minutes. Go, guys. Okay, there's still quite a few struggling on this, so let me just point out a couple things. We're going to go through all the answers. But number 1 is, because we are making comparisons, to make comparisons, I have to have something that is the same. If I don't have something the same, I can't actually compare. So to make them the same, that's why we went down to 1 square mile. This is what we call a unit rate. We haven't given you that definition yet. We will in about 2 lessons. But to make a comparison, I need to look at the same thing. So for all of these different ratios, our bottom line is we need to get to where we're comparing to 1 square mile. So we start with the information they gave us. In this case, I have 2 whole people, so that's 400, plus another half makes that 500. So 500 people. And we have 2 boxes, so that's 2 square miles. That should make it very easy. Again, when you set these up, if you will add in the labels immediately, it makes everything else easy. Because I now know I'm going down to 1. How do I go from 2 to 1? Divide by 2. So the 500 I need to divide by 2 to give me 250. New Jersey, there are 6 figures. That makes it 1,200 people. And there's only 1 box. So they gave me that one in simplest form. I can already do my comparison because I'm already at 1. So I don't have to do anything else to that one. Texas is the most difficult of all of them because we have 2 people, that's 400. That's 3/4 of a person. That makes it 175. So that gives me a total of 575 people. And there are 6 square miles.
Yeah, it would be 150.
Because 200 divided by...
Oh, you're right. Thank you. Good job. 3/4, yes. I did it right last class. People. And again, we're going to 1 square mile. How do I go from 6 to 1? Divide by 6. So I got to take 550 and divide by 6. So 550 divided by 6. That's going to go, we'll go there. It'll go 9 times. 54 gives me a 1. That's going to go once. Gives me a 4. Bring down another 0. That's going to go 6 times. 36. Oh, I'm now in a repeating situation, so I know that's repeating. So 91 and 6/10 repeating. We now have all the information we need in order to make a comparison. Because these are all out of 1 square mile, my denominators are the same. I can now compare my numerators to make my comparison. So when it talks about population density, it's saying how many people in 1 square mile, which one has the least population density? Oregon, because they're at 40. So Oregon has the least. The other question, which one has the most? New Jersey, 1,200 by a lot. The most or the greatest? Does everybody understand the process we went through? Better yet, does anybody not understand the process we went through? Maybe the better question. So there's really a couple steps to it. Step 1, you have to set up your initial ratio. So you have to be able to look at the figure, transfer it into a ratio. Number 2, I need to have the same thing to compare. So that's where we got to talk about unit rate, going down to 1. So whatever I need to do to get to 1, I have to do the same thing on the top. That keeps our fraction equal. Once I've done that, then I need to look at the numbers and actually make the comparisons. We have to use the math that we've done. Okay? Let's go ahead and go to our next page. Everybody should be on page 213. So this is where we're talking about using ratio reasoning to solve our problems. On our first one, your weight on Earth is a measure of the amount of gravitational attraction exerted by the Earth. The moon has a weaker gravitational force than Earth. So your weight on the moon is different than it is on the Earth because of that difference in gravity. So what we've done here, we have the ratio of weight on Earth versus the weight on the moon is about 60 to 10. They simplified it to make the numbers easier for you. And then they've now put it into a ratio table. So the ratio tables show how two quantities are related. These are another way to organize information. So just like we had with our double number lines, just like we've had with our fractions, just like we had with tape diagrams, ratio tables are now another format to display our data. On this one, they looked at this from two different ways. Okay? They looked at using multiplicative reasoning and said, okay, well, if I go from 60 to 30, that means I divide by 2. So I have to do the same thing to the bottom numbers. I divide 10 by 2 and I get 5. Does that make sense for everybody? Okay? That is what we call multiplicative reasoning. In multiplicative reasoning, I must use the same number on the top and bottom. You can also look at this as additive reasoning. The big difference is if I'm doing additive reasoning, I need to use the numbers from each separate category. So by that, what I mean, if I take 60 and I add the 30, add the two numbers together, what do I get? 90. That's additive reasoning. On the bottom one, now my numbers are 10 and 5. So if I add those together, I get 15. So did we add the same number? No, because up here I added 30, yes. Down here I added 5. I used different numbers. Does that seem wrong? It does if you're thinking from a multiplicative fashion. Multiplicative, we always have to use the same number. But in an additive format, I need to add whatever the value in that column and that row is. See how those values are different, right? So this one is going up by 30, so it's plus 30 from an additive. This one's going up by 5, so it's plus 5. That is your difference between multiplicative and additive reasoning. Multiplicative, I always use the same number, because multiplying that number by, because if you think about it, multiplication is repeated addition, right? So really what I'm saying, when I say divided by 2, is I'm saying what is half of this number? Half of 60 is 30. So when I add them together, I get that. Half of 10 is 5. So I do this. Okay? But if I'm using the additive reasoning, which is fully acceptable, I have to add the value for each row, which can be different and normally will be different unless it's a 1-to-1 ratio. Is everybody okay with that? That's a huge concept.
Basically the same thing with the double line, right?
Same as the double number line.
Has to be
What that line is.
line.
Okay? So verify that the three are equivalent. How can I show that 60 Earth weight over 10 moon weight is equivalent to the other two? The easiest way is what we just did in our initial problem. Go to a unit rate. If I make my denominator 1 or simplify as much as I can, then I can make a comparison. So if I have 60 and 10, how would I get to a denominator of 1? Divide by 10. So guess what I'm doing to the 60? Dividing by 10, which gives me 6. Okay? And let me just add a key because this is driving me crazy. So that's the pounds on Earth. And M is the pounds on the moon. Okay? What if I start at 30 Earth and 5 on the moon? How do I go to 1 on the moon? Divide by 5. So guess what I do to the 30? Divide by 5. What do I get? Does that look familiar? What if I do my last one, 90 and 15? 90 Earth, 15 Moon. I want to go down to 1. How do I go from 15 to 1? Divide by 15. So guess what I'm doing to the 90? Dividing by 15. And what do I get? So if I just shown that they are equivalent. How did I do it? By simplifying. So if they simplify to the same number, they are equivalent. That is actually the definition of equivalent ratios. You know that ratios are equivalent if they simplify to the same number. Make sure you have that written down, right, Richard? Oh, those papers look really interesting. Let's clean up your mess. Okay, has everybody got this written down? Okay, I'm going to pause the video for a second so you guys can finish writing. Okay, let's go ahead and go to our next page. So now we're going to look at different strategies. So Howard, let's try that again. Howard, Carla, and Mitsu, and Ralph all are looking at how to make a 120-pound person. So basically they're adding another column to the ratio table that we just built. Howard says, okay, well, if I'm going to go to 120, I can go back to 60. If I multiply that by 2, then I go to the 10. I also multiply it by 2. I know that that is going to be 120. Does that make sense? Yeah. Yes. So what I want you to write here, this is multiplicative reasoning. In other words, I'm using the operations of multiplication and division to go from one entry to the other. The key on multiplicative reasoning is whatever I do on the top, I must do on the bottom. I use the same number when I'm looking at it from a multiplicative aspect. Carla, who can tell me what format Carla used? What do you think, Zach? Double number line. So she took the table and turned it into a double number line and said, well, okay, if I need to get to 120, on this side, I'm going up by 30 each time. So I set up my double number line, made sure I did my interval the same across the top, but my interval on the bottom is different, right? My interval on the bottom is I'm going up by 5. So if I'm going up by 5 each time, now I just add 5 and I get to 20. So she used a double number line, just another format, and got to the same answer. Does her reasoning make sense to you? Anybody not understand her reasoning? Okay, so everybody's good on that one? Okay, Mitsu used a little bit different. He said, well, okay, I have 30 and 90. If I add those two together, I will get 120. But if I'm going to add those numbers together, I also need to add these two. So if I add 5 and 15, I get 20. So this is what we call additive reasoning.
Do these words look familiar? These are our vocabulary words, ladies and gentlemen. These are our vocabulary words, yes.
So additive reasoning is absolutely fine. If I have two numbers in one of the columns that I can add together to get the answer, I just need to add the same equivalent numbers from the other piece of the column. Okay? So if I'm putting those two together, I have to put those two together. That is your additive reasoning. Did I add the same number on the bottom that I did to the top? No, because in proportional reasoning, I have to add the pieces together. And that's the big difference between additive and multiplicative reasoning. Multiplicative, I will always use the same number on top and bottom. additive reasoning, I will be using different numbers because I'm using the individual pieces, which is where we turn the page and we get to Ralph's reasoning, and here's where we have the issue. Got to erase that from last class. Okay? So in Ralph's reasoning, he says the difference between 90 and 120 is 30, so I just added 30 to 15 to get 45. Okay? So, why is that wrong? Who can tell me? What do you think, Wyatt?
Because it's the difference between 90 and 120, not the difference between 15 and 10 and 5.
Good. Because each row has a different rule, correct? The rule on the top is I'm adding, going up by 30s, but the rule on my bottom is I'm changing by 5s. So you have to look at the rule by the row if you're going to use additive reasoning. Because he is using additive reasoning, my numbers are going to be different because it's based on what that row, the relationship within that row is. Okay? So what should he have added to 15 to get the same answer? 5. Because when I added 30 and 90, I have to add the same numbers on the bottom. Now, quick note. What if I wanted to get, and we're just going to use this as an example. So I'm going to add another row, and I want you guys to get to 180. Who can tell me how to get there? What do you think, Wyatt?
You can multiply 90 times 2, or you can add 30 to 120. Oh, wait.
30 to 120?
You can add, yeah. No. Yes.
No.
No.
What do you think?
So you add 60 to 120 and
Good.
10 to 20.
So I can add 60 to 120. So from an additive perspective, I can add those to get to 180. So if I did that, what numbers do I add on the bottom then? Let's just make a correction. This one should have been 20. So what numbers would I add on the bottom? 10 and 20. I have to use the same entries if I'm going to use additive. So 10 plus 20 would get me 30. I also like the initial thought. I could have also gone here and gone times 2. 15 times 2 would also get me 30. So there's a lot of different ways to get to your answers, right? Guys, here's one of the beauties of the ratio tables. Once I have my data, there are a lot of different ways to get answers. I can do a multiplicative entry from any point in here, or I can find an additive. I can find some way to add pieces together. I just need to make sure I'm adding this column, whatever row I'm using, I have to use those same entries from the top and the bottom, okay? I could have gone back to here and said 30 times 6, which would have been 5 times 6. I could have gone to 60 and said 60 times 3, which means I would have done 10 times 3. Are you starting to see how flexible these tables are?
Yes.
Okay? So this is really one of the beauties on the ratio tables, guys. They give you a lot more flexibility because there's a whole bunch of different ways I can approach my answer when I've got the ratio table. The downside is you have to have good entry data to build the ratio tables. Okay? And so we already did a comparison between Howard and Carla's strategies, right? So Howard and Carla. Howard was using multiplicative reasoning. Which type of reasoning is Carla using when she does a double number line? Additive. So I didn't add that, but this is really additive reasoning. So to me, that would be the easy way to answer number 3 there. Howard used multiplicative reasoning. Carla used a double number line with additive reasoning. Lattes inform me that I write way too fast and I need to actually pause so that you guys can catch up. So I set this up to you, Zach. I set this screen up so you should be able to see it. Oh, that's not good. Okay, guys, any questions on how we're doing this so far? So, explain Mitsu's reasoning. What did Mitsu do? He used additive reasoning. So he used the individual entries and just made sure he used the same number from the same entry. Okay? Then, how can we verify that that is a correct equivalent ratio? What do you guys think we should do? Who remembers what I said is the definition of equivalent ratios? Simplify. So I take 120 pounds on the Earth, so we'll just go back to my E&Ms, and 20 moon. What can I simplify both those by? 6. So that could give me 20, and I can't divide 20 by 6. We need a better number than 6. 4. Guys, as soon as I see a 0, the first thing I'm going to do is tens. That's going to give me 12 and 2, which should also give an easy one. So now it's 6 and 1. So was that the same as the other ratios we had? Yes. And Mitsu used additive reasoning. What? Guys, we really shouldn't be leaving within class within the last 10 minutes unless it's an absolute emergency. And then, what did Ralph do wrong? Vivian? Good. He tried to apply multiplicative reasoning to additive. It doesn't work. Okay? So, he tried adding the same number. Instead of the equivalent value. So remember, guys, that's really the huge difference between our multiplicative reasoning and our additive reasoning is, in multiplicative reasoning, I must use the same number. I have to multiply or divide the top and the bottom by the same number to go from one entry to another. In additive reasoning, I must use the value from that portion of the ratio. So it will be different in additive reasoning. I'm not adding the same number. I'm adding the same value. So I'm comparing the values in those to add them. That is the biggest difference. Any questions on anything we've covered today, guys? Is this making sense to you? Okay. Homework tonight is just a couple more Matthew workspaces. You should be at 36 total. So it should be relatively easy for you. Good luck.